Hello again. What we're going to do is some more theory on linear regression, and now we'll generalize the theory to essentially accommodating many inputs and one output, at least for now. And what we will present, but not necessarily derive in this video, is a general analytical formula that sort of applies to a lot of different linear regression problems. Okay, consider our usual linear regression problem. We have data xi and yi, where I is 1 to n. There are n data points, and xi and yi are real numbers. And we want to fit the best fit sort of model, y equals b naught plus b1x, okay? Just a straight line. So what would we want when we have such a fit? Ideally, we would like the following to be true. If we have n data points, we would like each of those data points, if possible, satisfy this equation, right? So b naught plus b1x1 equals y1, b naught plus b1x2 equals y2, and so on. Okay. Later on, we will see that maybe there are good reasons for something like this to be not true for more complex models, but let's go with this for now. Okay. So we would like all the data points, perhaps, to satisfy these equations. Well, at least these equations will be satisfied if all the data points lie on the straight line. Okay, then we notice that all these equations are linear in B naught and B1. Okay, so I'm just highlighting B naught and B1. They are all linear in B naught and B1. What that means is B naught and B1, there is no square or cube, or it's not sitting inside a trigonometric function like sine or cosine, no logs, etc. Right? So it's linear in these equations, in these variables. Okay. Because they're linear in these variables, we can rewrite these n equations into this matrix form, right? So we have this matrix, which is an n by 2 matrix. And then we have this matrix, which is a 2 by 1 matrix, and then this matrix, which is an n by 1 matrix. Okay? And these are the unknowns. This I would call the matrix of inputs, and this is the matrix of outputs. Now we can write this equation in this form, where we identify this matrix with the big X, this matrix with big Y, and this matrix with uppercase B. Okay. So we have this equation. We have this one matrix equation in these two unknowns, two scalar unknowns. Okay, and we can write that big X, uppercase X, belongs to R n cross 2. Right. So this is how we write n by 2 matrices. N by 2 matrices containing real numbers. This is the notation for that. And like we discussed before, this symbol means belongs to the set of, or is a, I think would be reasonable English translations of this symbol. So you would say B belongs to R2, or B is in R2, or B is a 2 by 1 matrix, I guess would be a reasonable thing to say, at least informally. Okay, so we have this matrix equation. We need to solve for B. Now, of course, the issue is that we have n equations in two unknowns. We have n equations in two unknowns, where n is typically greater than 2. We have many more data points than there are unknowns. If there are just two data points, then of course we can fit a straight line between them. There's a unique straight line. But if there are n data points, not necessarily lying on the straight line, then there's typically no exact solution for B, right? And that's what we've been doing so far. So what should we do? We should minimize the mean squared error, right? So there is no single straight line that passes through all the points, so we should minimize the mean squared error. And this is the mean squared error expression that we saw earlier. Let me move this away. This is the mean squared error that we saw before, right here. And it turns out that we can write this mean squared error expression, which we've used quite a bit so far, in terms of these matrices, okay? In terms of these matrices. Um, so instead of doing the summation, we can replace the summation as a matrix multiplication, okay? As a matrix multiplication. So we just replace this sum of squares with this matrix transpose matrix. I'm going to leave this as an exercise, at least for now, for you to show it. It's relatively straightforward to show it. Really, all you need to note is that if you have a column vector A, A1, A2 till AN, then if you go A transpose, which is this matrix, times A, and you do a matrix multiplication of these two things, of course, you get A1 square plus A2 square, etc. You get a single scalar, right? And this is exactly in that same form. Y minus xb is a column vector, and then you do transpose y minus xb, you get this, exactly like this, okay? So that's really the proof. Okay, so the idea is that you can write the mean square error in this form. And then I'm just going to present the final answer, and I will post a separate video that proves this final answer. If you want to find B that minimizes the mean square error, where this is the expression for the mean square error, then it turns out that the expression for the optimal mean square error, that optimal value of B that minimizes mean square error is this. X transpose X inverse X transpose times Y. You can verify that the sizes of the matrix are such that this is a legal expression, okay? Just make sure that that's all the matrix multiplications will work and so on. Okay, and it will turn out that this expression will work if X, the big X matrix, has more rows than columns, and the columns are not linearly dependent. Okay, so that's a technical caveat that we will talk about when I talk about the proof briefly. But essentially, this matrix needs to be invertible, and if you have reasonable data, it will be invertible. Okay, so that's it. This is the analytical expression. And recall that we derived a different analytical expression for B0 and B1 in an earlier video. This one is more special. So that analytical expression was specific only, it turns out, to this particular problem. This one, as we will show in a minute, is actually much more general. Okay, so you can check that this expression works by using MATLAB, let's say. So if you want to implement this MATLAB and you have lists, X list and Y list, then the big Y matrix is just Y list. And the big X matrix is a list of ones. If you recall, let me just go here. It's a list of ones and then a list of X's. So how would we write something like that? We can write it as the list of ones here. The list of ones needs to be exactly the same size as X list and then X list. Okay, so that's basically your big X matrix. And then once you have that, you can use this expression to derive the value of B. It turns out that if you have an expression like the equation like this, xb equals y, then B can also be derived in MATLAB by using the so-called backslash operator. You just go B equals x backslash y, and that just works. And it turns out that secretly, MATLAB is, when you say backslash, it's actually doing something equivalent to this when the number of rows of x exceeds the number of columns of x, okay? It's essentially solving a least squares problem when you do backslash, okay? So backslash, this is this operator, in case you have not seen, does a variety of things, it turns out. It can solve a system of linear equations, but it can also solve these least squares problems, essentially. by doing something like this. Okay, now of course, if you have an equation like this, you're not allowed to say b equals inverse of x times y, because the regular inverse of x does not exist. Okay, because it's no longer a square matrix, a regular inverse does not exist, so you're not allowed to do that. All you are allowed to do is this backslash, which, like I said, solves this least squares problem. This quantity, which essentially pre-multiplies y. So if x were invertible, it would say b equals inverse of x times y. But in this case, our correct expression is this more complicated thing. So what takes the place of inverse is this more complicated expression in terms of x. And that's actually called a Moore-Penrose pseudo-inverse, named after the two people that independently supposedly invented it. It's a generalization of the notion of an inverse. Um, and again, I will talk more about this when we do the proof of this expression in a different video. Um, but just again note that x inverse is not defined unless x is squared, but this Moore-Penrose pseudo-inverse is defined, even if x is not squared. And like I said, it's invertible only when x satisfies certain conditions, this thing. Okay, what's next? We just saw two more methods for solving this linear regression problem. We already saw fitlm in the first few lectures, and then we saw this analytical formula, and then we also saw backslash in MATLAB. All of these are essentially equivalent, at least for problems with a relatively low number of unknowns. It turns out MATLAB has, like I said, a few different functions that do relatively similar things. Regress is another function that does the same thing, except its syntax is a bit different. It puts the y matrix in front of the x matrix, and unlike fitlm, the x matrix for regress does include a column of ones. For fitlm, the x matrix does not include a column of ones. Okay, so you have to be careful about how you use these different functions. And like I was saying, this formula, x transpose x inverse, x transpose y, is quite general and applies even when we have multiple inputs. So what we saw just now was just a single input x, but it applies, it turns out, even if we have multiple inputs. Okay, so how does that work? Linear regression with multiple outputs. So imagine that we have two inputs, pi and qi, and one output, yi, each of which is a real number, and we have n such data points. And we want to find a relationship, a linear relationship between y and p and q. And let's say we write the linear relationship in this form, b0 plus b1p plus b2q. Let's call the list of y's y list. B is just b0, b1, b2. There are three unknowns now. And then we can write this equation for each of the data points in terms of the same expression as before, x times b equals y, where now x is now this matrix, list of ones, list of p's, list of q's, which we can write it in this form. This list of ones is one's size of p list, and then this is p list, this is q list. And again, once you've defined the x matrix, y matrix, and b matrix like so, and then we have this equation xb equals y, b that minimizes the mean squared error for this equation is again given by the same expression. And like I said, again, the same as x backslash y, or regress y comma x. And then, like I just said, if you want to use fitlm instead of regress or this Moore-Penrose pseudo-inverse method or backslash, if you're using fitlm, you have to drop the columns of y, because fitlm implicitly assumes that there is a constant term. Okay, but yeah, so these are just four different methods of solving essentially the same problem of finding the optimal values of b. b0, b1, and b2, okay, in MATLAB. So what we just saw is two inputs, one output. Of course, having two inputs and one output, or many inputs and one output, is sort of a general version of using polynomial models, if you will, right? So imagine we already saw how to fit polynomials with fitlm. So if you have y equals b0 plus b1x plus b2x squared plus b3x cubed, where you have this data set xi and yi, where I goes from 1 to n, then we can write this expression for each of the data points. We have a bunch of equations like this. And of course, we can write these equations as y equals x times b, where y is this matrix, the y list. The x matrix, the big X matrix, is this matrix consists of ones, x's, x squares, x cubes, and so on. And then b, of course, is the list of b's. And again, we can solve this problem using b equals x backslash y, or this Moore-Penrose pseudo-inverse times y, or regress y comma x, or and like we discussed last time, fitlm actually provides a simpler way of doing these higher order models. You just go x list comma y list, and then within quotes, I think, put x cubed. Or you can also list the actual columns and then try to find the optimal values of the coefficients. Okay, so what did we just show? We just showed that fitting this polynomial model is just a special case of fitting a model with multiple inputs, P, Q, R, S, T, whatever, and one output Y, okay? Exactly the same idea. So you can imagine, for instance, you have a quadratic model, but now in two inputs. So Pi and Qi are inputs, Yi is output. What's a general quadratic model in two inputs and one output? You have b0, the constant term, linear term, and all the quadratic terms, p square, q square, and pq. So for this, of course, the output matrix is the same. The input matrix is 1's p, q, p square, p times q, q square, right? So we can not only do these polynomial type models, we can also do any number of different nonlinear approximations, okay? So notice that these are all nonlinear approximations, but they all reduce to linear problems, essentially, okay? What's called linear least squares problems. Because the central equation looks like x times b equals y. What you get is a linear system in some sense. Okay, so how do you do Fourier series? Let's say you have data of the form ti, yi, right? And we suspect, so let's say t is time, y is some output, both real numbers. And we suspect that y of t is periodic in t with some known frequency f, okay? So the frequency is known. Then we can, if we have data like this, we can find essentially a Fourier series approximation of this form, where y is a0 plus a1 sine 2 pi ft, b1 cosine 2 pi ft, a2 sine 4 pi ft, b2 cosine 4 pi ft, etc., right? So where now if you want to write this in the linear regression form, we have y equals y list. B, the list of unknowns, is just now all these coefficients, a0, a1, b1, a2, b2, etc. And then x is all the terms multiplying these coefficients, list of ones for the constant term. And then for the sine term, you go sine 2 pi ft list. For the cosine term, you go 2 pi ft list, right? So these are all n by 1 columns, etc., right? And once you have this, you're done. You just do exactly the same thing, x backslash y, you get the value of b, or you can use regress or the pseudo inverse or fit lm, whatever. Now, why does this work? This works because the equation that we are writing, right? This equation that we're writing is actually linear in the unknowns, a naught, a1, etc., right? So it's non-linear in the actual inputs and outputs. Well, it's linear in the outputs, but it's certainly non-linear in the inputs. Um, but it's linear in the unknowns that we're trying to solve for. Because it's linear in the unknowns, all these problems essentially are the same. Okay. Now it's linear in the unknowns only because we know the frequency f, right? So notice that the frequency is sitting inside the sine or the cosine or all these trigonometric functions. This equation is linear in the unknowns only because we know the frequency. The frequency is also an unknown. In other words, we know it's a Fourier series, or we know it's some function of summation of sines and cosines, but we do not know what the frequency is. Then it becomes a non-linear problem. We cannot quite use the same method, or at least the same formula. But we can do a couple of related things. If we do not know the frequency f, what we can do is, well, switch to solving what's called a nonlinear least squares problem, essentially using some kind of general optimization method, which we will talk about in a few lectures. Alternatively, what we can do is we know how to solve this problem if we know f, know the frequency f. So what we do is we just fix the frequency, solve the problem, find the values of b, and then do that for different values of the frequency and see what the mean square error is for all the different values of the frequency and see which frequency minimizes the least square error, mean square error, right? So that's essentially another way of solving this nonlinear least squares problem and determining the frequency as well. Okay, so let me stop there. And then let me just briefly say that, again, I just gave this example of Fourier series, but you can imagine putting in any really complicated function there. It can be incredibly complicated. It can be however complicated as a function of these input variables, as long as there is no unknowns inside there. If the unknowns are just outside these complicated functions, then that is a linear problem, and you can solve all those problems using exactly the same formula or exactly the same functions. Okay, so this is a remarkably general approach for fitting pretty complicated nonlinear functions between inputs and outputs using essentially linear techniques.